Higher physics, particles and waves, interference patterns. Key areas. Maxima and minima are produced when the path difference between waves is a whole number of wavelengths or an odd number of half wavelengths respectively, and carry out calculations of the above. What we will do today is identify the interference patterns for both maxima and minima and carry out calculations. Maxima. In an interference pattern, we see points of maxima as bright spots if it's light, or loud sounds if it's sound, or potentially high readings if we have a microwave emitter. An interference pattern formed by two coherent sources will produce a maxima where we have points of constructive interference. Remember the rule for this: path difference equals m lambda for a maxima, where m is an integer, lambda is the wavelength, i.e. path difference is lambda, 2 lambda, 3 lambda, etc. Note that the space between each maxima is also equal to 1 wavelength, though this isn't specifically required for the higher course. Minima. Minima occurs at points of destructive interference, that is, the waves meet out of phase. Remember the rule for minima is the path difference is equal to m plus 1/2 lambda, i.e. the path difference is half a lambda, 1.5 lambda, 2.5 lambda, etc. Example. Find the wavelength of the waves used below if the second off-center maximum occurs at A. Here is our diagram. We saw waves coming from two sources which we're assuming are coherent, and we have a path between S1 to A and S2 to A, and these paths are different and shown in the diagram. If you remember from the previous video, the first thing we need to do is to find the path difference. The path difference between the two waves is 36 minus 24, which is 12 centimeters. We're told in the question that we're looking at the second off-center maxima. Remember the first maxima, the central maxima, occurs when the path difference is equal to 0 lambda. We sometimes call this the zero order maxima, and that's here. Then our first order maxima, where we have our first maxima above the central point, is 1. And then at our second maxima, second order maxima, we're at 2 wavelengths. So the path difference is increasing as we move up from the 0 line to up to the A, and the points of maxima occur every time we increase by 1 wavelength. 0 wavelengths, 1 wavelength, 2 wavelengths. So m in this case is equal to 2. Remember, for a maxima, path difference is equal to m lambda. So lambda is equal to the path difference divided by m. In this case, 12 divided by 2, which gives you 6 centimeters. For the purposes of looking at examples, we're going to look at some past paper questions from the old higher course, multiple choice questions, and some from section B. You could pause the video just now and have a shot at doing these questions yourselves, but we're going to go over these questions in the next few slides. (2000) paper question 14 in the multiple choice section. Waves from coherent sources S1 and S2 produce an interference pattern. Maxima of intensity are detected at the positions shown below. The path difference S1 to K to S2 to K is 154 millimeters. So path difference is equal to 154 millimeters. We're asked to find the wavelength of the waves. Now, in order to find the wavelength of the waves, we must first find out m. Well, a central maximum occurs when the path difference is equal to 0 lambda. The next one is at 1 lambda. Our next one's going to occur at 2 lambda, 3 lambda, 4 lambda, and then at k, we're at 5 lambda. So m is equal to 5. Remember the rule for constructive interference. Path difference is equal to m lambda. In this case, our path difference is 154 millimeters, and this is equal to 5 lambda. So lambda is 154 divided by 5, which gives you 30.8 millimeters. D. (2001), question 15. S1 and S2 are sources of coherent waves that produce an interference pattern along the line xy. The first maximum occurs at point P, where S1 to P is equal to 20 centimeters, S2 to P is equal to 18 centimeters. For the third maximum at R, you need to find the path difference. Well, if P is the first maximum, M is equal to 1. So the path difference, being equal to m lambda, is going to be just equal to lambda. The path difference is going to be 20, take away 18, which is equal to 2 centimeters. So lambda equals 2 centimeters. We're looking at the third maximum, so m is equal to 3. Path difference is equal to m lambda, which is 3 times 2 centimeters, equals 6 centimeters. D. 2004, question 14. Again, two identical loudspeakers, L1 and L2, are operated at the same frequency and in phase with each other, so they're coherent. An interference pattern is produced. At the position P, which is the same distance from both loudspeakers, so that's our zero order maxima, there is a maximum intensity. The next maximum intensity is at position R, so this must be our first order, where L1 to R is 5.6 meters and L2 to R is 5.3 meters. So our path difference is going to be equal to 5.6 take away 5.3, and because that's our first order maxima, I know this is equal to 1 lambda. We're told the speed of sound, v, is equal to 340 meters per second, and we're asked to find how we determine the frequency. Well, if you remember the wave equation as it appears on the relationship sheet, v equals f times lambda, which you can rearrange to f is equal to v over lambda. Substituting in what we already know from above, this is equal to 340 over 5.6 take away 5.3, which is C. (2008), question 14. A source of microwaves of wavelength lambda is placed behind two slits R and S. The microwave detector records a maximum when placed at point P. This is the central order maxima. The detector is moved and the next maximum is recorded at point Q. So point Q must be our first order maximum. The path difference SQ to RQ must be 1 lambda. That is C. (2012) paper, question 9. S1 to S2 are sources of coherent waves. An interference pattern is obtained between X and Y. The first order maxima occurs at point P. The third order maxima at R. For the third order maxima at R, the path difference is Well, we know at point P that our path is 200 millimeters from S1 to P and 180 millimeters from S2 to P. So the path difference at our first order is going to be 200 take away 180, which is equal to 20 millimeters, and that is equal to 1 lambda, because m is equal to 1. So lambda is equal to 20 millimeters. For the third order maxima, m is equal to 3. Therefore, path difference is equal to m lambda equal to 3 times 20, which is 60 millimeters. So very similar to the previous question. And you find that the questions are very similar as you go through the past papers. Let's have a look at a larger question. A student is using different types of electromagnetic radiation to investigate interference. In the first experiment, two identical sources of microwaves, S1 and S2, are positioned a short distance apart as shown. The student moves a microwave detector from X towards Y. The reading on the meter increases and decreases regularly. Explain in terms of waves what causes the minimum readings to occur. We're then asked for the third maximum from the central maximum located at P. The distance from S1 to P is 620 millimeters. The wavelength of the waves is 28 millimeters, and we need to calculate the distance from S2 to P. So let's take these one part at a time. So we've taken the diagram from the question for our key information. The student moves the microwave detector from X towards Y. We're told that the meter reading increases and decreases, and we need to explain in terms of waves what causes the minimum readings to occur. Well, we should know from our definitions, minima, keyword, occur when two coherent waves meet out of phase. Causing destructive interference. Part 2. The third maximum from the central maximum is located at P. So m is equal to 3 here, so our third order maxima. The distance from S1 to P is 620 millimeters. And the wavelength of the waves is equal to 28 millimeters. Calculate the distance from S2 to P. Well, let's put in our information. We've got our path from S1 to P there. Our wavelength is equal to 28 millimeters. And our order of maxima is equal to 3. So m is equal to 3. For a maxima, path difference is equal to m lambda, which is 3 times 28, which is equal to 84. So our path from S2 to P is equal to our path S1P plus the path difference. We're told the path S1 to P is 620 plus 84 gives you 704 millimeters. '14 paper, question 28b. In the second experiment, microwaves of wavelengths 30 millimeters pass through two gaps between metal plates as shown. The distance from each of the gaps to point J are shown in the diagram. Use this information to determine whether J is a point of constructive or destructive interference. You must justify your answer by calculation. Then in part 2, we're told the microwave detector is now moved to K, which is a point of destructive interference. Gap 1 is then covered with a sheet of metal, and you need to say whether the strength of the signal detected at K increases, decreases, or stays the same. Again, you must justify your answer. So let's take each question at a time. We need to find out whether point J is a point of constructive or destructive interference. So what we need to do here is we need to find the path difference and then compare that to the wavelength. The path difference in the question is going to be equal to 500 millimeters, take away 425 millimeters. That's just gap 2 to J, take away gap 1 to J, which is equal to 75 millimeters. The wavelength is equal to 30 millimeters, as shown in the question. 75 divided by 30 is equal to 2.5. Remember our conditions for constructive and destructive interference. For constructive interference, the path difference is equal to m lambda. For destructive interference, path difference is equal to m plus a half lambda. Here, the path difference is equal to 2.5 lambda. Therefore, we have destructive interference. Having a look at the second part, we need to determine if the signal strength is going to increase, decrease, or stay the same if we cover one of the gaps looking at point K where we know we have destructive interference. Now remember, for destructive interference, we experience a minima. The minima is occurring because part of the wave is being cancelled out, potentially all of the waves being cancelled out by another wave. So we get a low signal. If I cover over one of the gaps, gap 1, then I have only one single signal. There is no destructive interference occurring, therefore the signal strength will increase. As no interference is taking place.